All right, welcome back to the deep dive.
Yeah, excited to be back.
For today's deep dive, we're looking at something that you sent our way, and I've got to say, it's pretty relevant, especially given all the buzz around AI and code generation lately. We're going to be talking about security vulnerabilities and how well we can actually detect them in C code.
Absolutely.
Now, this paper, it doesn't shy away from the tough questions. It really digs into the reliability of all these different methods for spotting these vulnerabilities. Everything from classic static analysis to the newer large language models, the LLMs everyone's talking about.
Yeah, and I think that's what makes this paper so important. We're at this point where AI is becoming more and more involved in actually writing code, so we really need to be able to trust that the code it's generating is, well, secure.
Right, exactly. No point in having AI that can write code at lightning speed if that code is riddled with security holes.
Exactly. Yeah. And this paper goes a step further by providing a side-by-side comparison of all these different techniques, which is really valuable.
Mm-hmm.
They did this by using a benchmark they created called CASTLE. Have you had a chance to look at that?
Yeah, CASTLE, it stands for CWE, Automated Security Testing and Low-Level Evaluation, right?
You got it.
Seems like a pretty clever approach from what I gathered. Can you tell us a bit more about what makes this benchmark so special?
Sure. So the authors of the paper, they realized that a lot of the ways we've been evaluating vulnerability detectors, especially for C code, have some serious limitations. Like many of the older data sets out there, they don't have a good mix of different types of vulnerabilities.
Makes sense.
Plus, and this is a big one, a lot of that code isn't even compilable, which means you can't test some of the more powerful analysis methods like formal verification.
Ah, I see. So CASTLE addresses those issues.
Yeah, that's exactly what they set out to do. So they created this data set of 250 small, self-contained seed programs. Each program, it has just one specific vulnerability, and they pick these from a list of 25 of the most common weaknesses. Think of it like a controlled testing environment, where you can really compare how well different tools perform on the exact same set of challenges.
Oh, okay. So it's like having a standardized test ground for these security tools. Makes sense. And they didn't limit themselves to just testing a couple of methods, did they?
Oh, no, they went all out. They evaluated 13 different static analysis tools.
Mm-hmm.
Those are the ones that look for problems in the code without actually running it. They also looked at 10 of the top LLMs, those large language models we talked about. And to top it off, they even included 2 formal verification tools. Those use like mathematical reasoning to prove whether the code has certain properties.
Wow, that's really thorough. But with that much data, I imagine it gets pretty tricky to compare everything.
Yeah, and that's where their new evaluation metric comes in. They call it the CASTLE score.
Okay, a new scoring system. That sounds intriguing. What does this CASTLE score tell us that we wouldn't get from other metrics?
It's all about nuance. See, the CASTLE score doesn't just care about whether a tool found a vulnerability or not.
Right.
It also looks very closely at how many false positives it throws out. Those are the incorrect alerts, the ones that can really waste a developer's time.
Oh, yeah. False positives, the bane of every developer's existence.
Tell me about it. The CASTLE score actually penalizes tools that have a lot of false positives. And to sweeten the deal, it even gives bonus points for finding really critical vulnerabilities from the MITRE top 25 CWEs.
So it's not just about raw accuracy then?
No, it's more about how useful a tool would actually be in a real-world scenario. Where avoiding false alarms is just as important as actually catching the bugs.
Absolutely. So what were some of the big takeaways from all this testing? What did they find out about how these different methods actually perform?
The results were really interesting. They found that the LLMs, they're actually surprisingly good at spotting vulnerabilities in these smaller pieces of code. Probably because they're so good at picking up patterns from all that data they've been trained on.
So pattern recognition is their strong suit.
Exactly. However, their accuracy started to drop when they had to deal with larger code samples.
Ah, so they don't scale as well.
Right. Plus, they were more likely to, hallucinate.
Hallucinate? You mean like report vulnerabilities that aren't actually there?
Yeah, exactly. Now, the traditional static analyzers, they were better at handling those larger code bases, but they often had a high rate of false positives, which, as we said, can be a real pain.
Yeah, not very efficient if you're spending all your time chasing down false alarms.
Now, formal verification tools, they were the champions when it came to minimizing those false positives, especially for the specific vulnerabilities they're designed to catch. Like, they're great for memory safety issues.
Oh, that's good to know.
But the catch is they have more limited scope. So they might miss other types of flaws, like security problems in how the code handles data.
So each approach has its own trade-offs. Makes sense.
And to make it even better for other researchers, they've made the entire Castle dataset available on GitHub.
Oh, that's fantastic. It'll be interesting to see what other researchers can do with it. Now, let's rewind a bit and talk about the paper itself. What was the driving force behind this research? What problem were they trying to solve?
Well, their introduction does a really good job of setting the stage. They talk about how AI is rapidly advancing in the field of software development and even mention some predictions that, AI could soon be handling a lot of the coding process.
Yeah, we've all heard those predictions, AI writing all our code for us in the future.
But here's the thing, they also cite research, like this study by Tihani and others, that shows that code written by LLMs can often have security vulnerabilities.
So it's not all sunshine and roses with AI-generated code.
Right. And that leads to their central problem. If we're going to rely more and more on AI to write our code, how can we be absolutely sure that it's secure? We need to know which detection tools we can actually trust.
And that's no small feat, right?
No, it's not. The authors highlight a few reasons why this is such a tricky problem. First, there's just a huge variety of vulnerabilities that can exist in C code. You have things like memory corruption issues, logic flaws, all sorts of things.
Yeah, it's a complex landscape.
And then, of course, you have the LLMs, which are relatively new to the scene. We still need to figure out exactly what they're good at and where they struggle. And then there's the issue of standardized benchmarks, or rather, the lack of them.
So it's hard to compare these different tools apples to apples.
Right. They point out how a lot of the existing data sets have problems like they don't have a good balance of different types of vulnerabilities, or a lot of them don't even have compilable code, which makes it impossible to test some of the tools properly.
Okay, so their goal was to create a better benchmark.
Yeah, a more robust and representative way to evaluate these tools. And that's where their research questions come in.
Right, so what were those questions exactly?
They had three main ones. First, how do static analysis tools, formal verification methods, and large language models compare when it comes to finding vulnerabilities in C code? Second, are there any benefits to combining these different types of tools instead of using them one by one? And third, what are the best ways to actually measure and compare how well they perform? And from those questions, their main contributions were born: the Castle benchmark itself, and that whole evaluation they did using this benchmark and their new Castle score.
Very cool. So once they set the stage, they took a look at what other researchers have already done in this area, right? What did they find out from reviewing all that existing work?
They did a really deep dive into the existing research. And one thing they noticed was that a lot of the early work on AI in software development was mostly focused on whether the AI-generated code actually worked, functionally.
So did it do what it was supposed to do?
Yeah, security wasn't always the top priority. And when they looked at the existing vulnerability data sets, they found the same problems we talked about earlier. Uneven coverage of different types of vulnerabilities. Not enough balance between vulnerable and non-vulnerable code samples. And a lot of the data sets didn't even have compilable code.
So they saw a real need for something like Castle.
Absolutely. And they actually go through a whole bunch of existing data sets in the paper. It's like a little survey of what's out there.
Oh, that's handy. Which ones did they cover?
Well, they mentioned Draper, BigVul, DiverseVul, FormAI v2, PrimeVul, SARD, Juliet, Divine, Reveal, and CVE fixes.
Wow, that's quite a list. Did they go into any detail about them?
Yeah, for each one, they give a quick rundown of its main characteristics, like how big it is, whether it lets you have multiple vulnerabilities in a single file, if the code can be compiled, and how the vulnerabilities were actually labeled. They point out that while some of them, like SARD and Juliet, do have compilable code, the files can be really big.
And that can be a problem for some of the tools.
Right, especially for LLMs, which have token limits, and for formal verification tools, because it can take forever to run them on big files. They also talk about FormAI, which is labeled using ESBMC. Since ESBMC is a formal verification tool, it means that the dataset won't include certain types of vulnerabilities that ESBMC isn't designed to find.
So it's really important to have a dataset that's specifically designed to be comprehensive and avoid these limitations.
Exactly, and that's what makes Castle so valuable.
Okay, so they've covered the need for a good benchmark, and they've reviewed the existing datasets. What's next?
Then they shift gears and talk about the more traditional ways of finding vulnerabilities. ones that were around before LLMs became a big deal.
Right, the classic approaches.
Yeah, they give a good overview of static analysis techniques. Those involve things like looking for patterns of vulnerable code and figuring out how data moves through the program. They also talk about dynamic analysis methods like fuzzing. That's where you basically bombard the program with random inputs to try and make it crash.
Oh, yeah. I've heard about fuzzing. Controlled chaos.
Pretty much. And of course, they cover formal verification techniques like bounded model checking and theorem proving. Those use mathematical logic to try and prove whether the code is doing what it's supposed to do. They even mention the NIST-SARD evaluations, which have been used for years to assess static analysis tools on large, real-world software projects.
So it seems like even before LLMs came along, there wasn't a single perfect solution for finding vulnerabilities.
That's right. Different tools have always had their own strengths and weaknesses, and they often miss vulnerabilities or give false alarms.
So LLMs aren't entering a field where everything was already solved.
Nope, not at all. It's a complex field with a lot of challenges. And then the paper dives into the rise of large language models in this space. They point out that while LLMs are great at understanding code, they mostly find vulnerabilities by recognizing patterns from all the code they were trained on.
So they're good at spotting things they've seen before.
Yeah, which means they might struggle with vulnerabilities that are new or unusual, things they haven't encountered in their training data.
It's like they have a great memory for code, but they might not be so good at thinking outside the box.
That's a good analogy. The paper also talks about the newer decoder-only transformer models like ChatGPT and CodeLlama, and how techniques like prompt engineering and chain-of-thought reasoning are being used to improve their ability to find vulnerabilities.
Trying to make them a bit more clever.
Exactly. They also go into the different types of transformer models, encoder-only, encoder-decoder, and decoder-only, and point out that the trend is moving towards decoder-only architectures and in-context learning. That's where the model learns from the information in the prompt without needing to be retrained.
Interesting. So they're becoming more adaptable.
In a way, yes. And while some studies have shown LLMs doing better than traditional tools on some benchmarks, the authors emphasize that this doesn't always hold true for all types of vulnerabilities or for larger, more complex code.
Okay, so context matters. So that gives us the background. Now let's get to the nitty-gritty. How they actually design and use the Castle benchmark to test all these different tools. How did they go about that?
They were very thorough in their methodology. When creating the Castle dataset, they started by choosing the right common weakness enumerations, those CWEs we talked about. They focused on the ones that are relevant to C code. Then they had cybersecurity experts manually create both vulnerable and non-vulnerable test cases for each CWE. This manual review process was crucial to make sure the benchmark was accurate and relevant.
So each test case was carefully crafted.
Yeah, it was a lot of work, but very important. The final Castle dataset has 250 small C programs covering 25 different CWEs. There are 10 test cases for each CW6 with a vulnerability and 4 that are secure. And every program is designed to be compilable and to have either one vulnerability or none at all.
So very controlled and consistent.
Exactly. They also included a metadata block at the beginning of each file, formatted in YAML. That metadata tells you things like the CW classification and the exact line of code where the vulnerability is. The paper even gives you stats on the code complexity, like the average length, the number of functions, and things like cyclomatic complexity.
To show that it's not just trivial code.
Right. Even though the snippets are small, they still have some internal complexity.
Right.
And Table 2 in the paper, it lists all 25 CWs they included and how they relate to the Mattery Top 25 list, just to show that they focused on the most important vulnerabilities.
Got it. So they had this carefully designed data set. How did they actually run all these security tools on it?
Automation was key here. They developed custom software wrappers for each tool. Think of them like translation layers.
Okay.
For the open source tools like Clang Analyzer and ESBMC, they use Docker containers to create a consistent environment for running the tests. Then they use Python scripts to automatically run each tool on every test case in the dataset and to parse the output into a standard format that they could analyze.
Smart.
For the closed source tools, they had to use the proprietary APIs or upload the code to their online platforms, and then their scripts would fetch the results. And for the LLMs, they used the OpenAI APIs and crafted specific prompts to tell the models to find vulnerabilities and give their findings in a structured JSON format.
So they had to be creative to get everything to work together smoothly.
Yeah, it was a pretty impressive engineering feat. And the best part is they made all these wrappers available on GitHub so other researchers can use them too.
That's awesome. Okay, now we get to the heart of it, the Castle score. How do they actually calculate it, and what are the different things that factor into it?
The Castle score, it's meant to be a more well-rounded measure of how well a tool performs. For each test case, a tool gets points for correctly finding a vulnerability, and they get bonus points if that vulnerability is one of the really bad ones from the MITRE Top 25. The higher it is on that list, the more bonus points they get, up to 5.
So they're incentivizing finding those critical vulnerabilities.
Right. And they also get points for correctly identifying code that doesn't have a vulnerability.
Yeah.
But here's the kicker. The score goes down for every false positive.
Ah, so they're really punishing those false alarms.
Yep. And the formula even includes penalties for reporting extra incorrect vulnerabilities in code that already has a real one. So if a tool finds a real problem, but then throws out a bunch of false alarms, it'll still get a lower score.
Makes sense. So they also had a Castle combination score, right?
Yes. That's for when you use multiple tools together. It takes into account any overlap in their findings and makes sure the penalties for false positives from each tool are included.
Okay, so we have the benchmark, the tools, and the scoring system. What happened when they actually ran the experiments?
Time for the results. They analyzed the static analyzers, the formal verification tools, and the LLMs separately. They did this to really understand what each category was good and bad at. Looking at the tools individually, ESBMC, which is a formal verification tool, got the highest Castle score overall. They think this is because formal verification is really good at avoiding false positives, at least for the types of vulnerabilities it's designed to find, which are mostly memory safety issues. But they also point out that ESBMC isn't meant to find things like SQL injection or problems with cryptography.
So it excels in its niche.
Exactly. Another formal verification tool, CBMC, it had 0 false positives, which is amazing, but it also missed a lot of the real vulnerabilities.
So super accurate, but not very comprehensive.
Right. Among the static analyzers, CodeQL did the best. It found a good amount of the vulnerabilities while also keeping the false positives relatively low, especially compared to other tools like SonarQube, which found about the same number of real issues but had way more false alarms. Some tools, like Clang Analyzer and CBMC, were very precise. When they said there was a vulnerability, they were usually right. But they missed a lot of others. Then you had tools like Splint and CodeThreat, which had tons of false positives, so much so that they ended up with negative Castle scores.
Ouch, not a good look. So it's clear that there's a trade-off with each type of tool. Formal verification is very precise but limited. Static analysis is broader but noisier. And what about LLMs? How did they stack up?
The LLMs actually did pretty well overall. GPT-03 Mini got the highest score out of all the methods they tested. They were good at finding a lot of the known vulnerabilities in the small code snippets. Interestingly, while some of the bigger LLMs, like GPT-40, found more of the real vulnerabilities, the ones that seemed to use more advanced reasoning techniques had fewer false positives.
So a bit more thoughtful in their approach.
Yeah, and that led to better precision. The authors concluded that LLMs are pretty good at finding vulnerabilities in these short self-contained C programs, probably because of their ability to recognize patterns from their training data.
Yeah.
But they also made it clear that this doesn't mean they'll be just as good when you give them larger, more complex code bases.
Okay, so don't overestimate them just yet. And speaking of limitations, what did the authors say about the limits of their own work?
They were very upfront about the limitations. First, they acknowledged the scope of the microbenchmark itself. While Castle has 25 different types of vulnerabilities, each test case is focused on just one vulnerability in a relatively isolated piece of code.
It's a simplification of reality.
Exactly. Real software is much more complex. So how well these tools perform on Castle might not perfectly reflect how they do in a real-world setting. They also did some preliminary testing with a bigger synthetic C program and saw that the LLM started reporting more false positives and even missed a known vulnerability.
So they struggled with the increased complexity.
Yeah, and formal verification tools also have trouble with larger code bases because of something called state explosion. Static analyzers, on the other hand, are generally better at handling larger projects, although they still have that issue with false positives.
Right.
Finally, they brought up the possibility of overfitting, where tool vendors might start tweaking their tools to do well specifically on Castle.
So it's important to keep the data set fresh.
Definitely. And they also mentioned that LLMs, being probabilistic, can have some variability in their results, unlike the more deterministic static analyzers.
So while Castle is a valuable benchmark, it's not a perfect mirror of reality.
Exactly. But it's still a major step forward. The authors wrapped up by summarizing what they learned from their research. They said that LMs are effective on small code but struggle with larger code. Static analyzers are broader but noisier. And formal verification is very precise but limited in scope. They also stress that combining different tools can lead to better results, especially when the tools have complementary strengths, like they saw with ESBMC and CodeQL.
So a diverse toolkit is the best approach.
That's what the evidence suggests. And they argued that the Castle score is a good way to compare these different tools because it considers both correct and incorrect findings, as well as the severity of the vulnerabilities.
Okay, a more holistic metric.
Right. They concluded by saying that future research should focus on dealing with the scalability issues of LLMs and formal verification on large code bases, and on figuring out how to best choose and combine different vulnerability detection techniques in practice.
So still a lot of work to be done.
Always is in this field.
It's really fascinating stuff, though. This paper really gets you thinking about the future of software security. And speaking of thinking about the future, it's time for our Novel Notions segment. Based on what you've read in this paper, what kind of unconventional research ideas pop into your head?
This paper definitely sparked some ideas for me. The first one comes from the fact that each approach, LLMs, formal verification, static analysis, they all have their own strengths and weaknesses. It makes you think, what if we could create a system that could automatically choose the best tool for the job?
Like an AI security analyst that knows which tool to use in each situation.
Yeah, exactly. Imagine you're a developer and you make a small change to your code. This intelligence system could quickly analyze that change using an LLM that's specifically trained for that kind of code. But then let's say you have a larger, more critical module that needs a thorough check. That could be sent to a static analyzer or even a formal verification tool, depending on how sensitive it is.
So it's about dynamically adapting to the situation.
Right. And we could even train a model using datasets like Castle and data from real projects to predict how well different tools will perform on new code. This model could learn when to trust an LLM, when to use formal verification, and when to go with static analysis.
So it's like having a team of expert AI security analysts, each with their own specialty.
That's a great way to put it. And this kind of approach could help us get around the scalability problems of LLMs and the noise problems of static analyzers.
That's a really compelling vision for the future of security analysis.
I think so too. And my second idea is about the fact that LLMs are basically pattern recognition machines. They've learned from a massive amount of code, which unfortunately includes code with vulnerabilities. This makes me wonder, could we trick them? Could we create adversarial attacks that introduce vulnerabilities in a way that LLMs won't detect?
Oh, that's a scary thought, like hiding a vulnerability in plain sight.
Yeah. And then the next question is, how can we make LLMs more robust to these kinds of attacks? Can we design them in a way that makes them less susceptible to these tricks? Or can we come up with smarter ways to prompt them so they don't get fooled?
So it's like an arms race between security researchers and attackers, but in the AI domain.
Exactly. And this research could borrow ideas from adversarial attacks in image recognition and natural language processing. Understanding these potential weaknesses in LLM-based code analysis is crucial if we want to use them in really sensitive applications.
It's a reminder that AI isn't a silver bullet. We need to understand its limitations and potential vulnerabilities.
Absolutely.
Well, those are some thought-provoking ideas. Big thanks for sharing them and for taking us through this paper.
My pleasure.
For everyone listening, if you want to learn more about the methodology and all the interesting results we talked about, we'll have a link to the full paper in the show notes. And on that note, here's a final thought to chew on. Given all the trade-offs we've discussed between LLMs, static analysis, and formal verification, how do you think software development processes will need to change in the future to effectively use all these different tools and create truly secure applications? That's something for you to ponder. Thanks for joining us for this deep dive, and we'll see you next time.